So, problem 7.3 is on your screen now. Let's have a look at this problem. We are given a state space model x dot equal to ax plus bu, where the model matrices A and B are given. We are asked to find values of q, small q, for which this gain matrix F is optimal in the sense of some capital Q and some capital rho, such that this F minimizes the cost V. It's important to understand that this is some sort of an inverted question. We're not given a cost and asked to find the gain vector F. We are instead given the structure of F, which is done here, and we are asked, is there a cost V with reasonable Q and rho? By reasonable I mean Q positive semi-definite and rho positive. So is there such a cost for which such a form of F would be optimal? And that's the question. So what we know is that if we have found some positive definite P such that it solves the algebraic Riccati equation, and the closed loop matrix is Hurwitz, then we know that that is the unique solution, and U given by this state feedback law is the optimizer for the given cost. We also know that such a P exists if the system is controllable and observable in the sense of the matrix Q. Now we can just use this to write down the algebraic Riccati equation. Note that we are looking for a symmetric positive definite P. So the variables here are P1, P2, P2, P3. So we have three variables. We also want P to be positive definite, which means P1 has to be strictly positive and P3 has to be strictly positive. This is because we want 1, 0, P 1, 0 to be positive and 0, 1, P 0, 1 to be positive. We also want the determinant. So if both the eigenvalues are positive, we know that the determinant of P is the product of eigenvalues of P, and P positive definite means that all eigenvalues of P are positive, which means that the determinant of P is positive. So we also have that determinant of P, which is P1 P3 minus P2 squared, has to be positive. Now Let's write down the algebraic Riccati equation. So we can simplify this further to obtain and finally so now we additionally know that f has to be of this form -1 and minus q, and we know that the optimal f is given by minus r inverse p transpose p, which is nothing but minus 1 over rho 0 1 p2 p3. So what we have is f should be of this form, which is nothing but minus p2 over rho and minus p3 over rho. So this means that p2 must be equal to rho, and p3 must be equal to rho times q. So now with these additional constraints, let's look back at this algebraic Riccati equation. What we obtain is so now we get a parameterization for q, which is given by rho q minus p1, rho q minus p1, and rho q squared minus 2 rho. So now what we want to impose is two things. One is that P is positive definite, which means P11, what we just saw, P11 positive, P22 positive, and determinant of P positive. And we want to impose Q positive semi-definite, meaning Q11 semi-definite, Q22, rather because it's now just a scalar and non-negative, and determinant of Q non-negative. So this is what we will start imposing on our parameterization and check what values of Q are feasible. So let's first look at these three conditions. So what we know is P now is given by, because we know that P2 is rho and P3 is rho Q, we still have P1 as the free variable. So our P is of the form P1 rho Q. So we need additionally P1 to be positive. We need rho Q to be positive, and because rho is positive, we need Q to be positive. So this is the first condition that we obtained on Q. Now, additionally, we need determinant of P. Let me write it here. Determinant of P, which is rho Q times P1 minus rho squared to be positive. We can clearly see that can choose P1 large enough so that this is satisfied. So now let's look at the conditions on Q. The Q parameterization we have here is this one. So we want rho to be positive, which we already have. Then we want rho Q squared minus 2 rho to be positive, which is nothing but rho times Q minus Q squared minus 2 to be positive, which means we want Q squared to be greater than 2, which means we want Q to be either greater than root 2 or Q to be less than minus root 2. Here we have some more conditions on Q. So note that we here want only non-strict inequalities for Q, which gives us these two additional conditions. Now the third condition that we want is that the determinant of Q, which is nothing but rho times rho Q squared minus 2 rho minus rho q minus p1 bracket squared to be greater than or equal to 0, non-negative. This is nothing but rho squared times q squared minus 2 minus rho q minus p1 squared to be greater than 0. Now p1 is still our free variable, so we can choose p1 to be equal to rho times q. So that gives us determinant of q, which is equal to rho squared q squared minus 2 is now greater than or equal to 2, because this was one of the conditions that we saw earlier, which is this one. So if q is greater than or equal to root 2 or q is less than or equal to minus root 2, this is positive or non-negative, and this is strictly positive. So we have determinant of q to be non-negative as well. Now we have to verify whether this choice of p1 is valid with our previous conditions. So now let's collect all the conditions that we had. So the conditions on q are as follows. Q has to be greater than 2 or less than minus root 2. Then we have q has to be positive strictly. And then we have this additional condition on p1, which is that p1 has to be greater than rho over q. And then additionally, we picked p1 to be equal to rho times q. Now, these three conditions tell us that q necessarily must be greater than or equal to root 2, because if this is not the case, at least one of the conditions is not fulfilled. Now if q is greater than or equal to root 2, which is almost equal to 1.41, we have that 1 over q is less than 1, which is less than q. And therefore we have that rho over q is less than rho q, which is what we set our p1 to be, and therefore p1 is greater than rho over q, which is just telling us that this condition is satisfied when we pick p1 as rho q. So to conclude, what we have is, if q is greater than or equal to root 2, we can have p, which is given by rho q, rho, rho, and p3 was, I think, q, q rho. Is positive definite and satisfies the algebraic Riccati equation with q given by which is nothing but because we've chosen P1 to be row Q, the off diagonal entries go away, and we have and now because P is positive definite, we know that it leads to a stabilizing solution. Yeah, so that's it for this problem. Thanks a lot.